Great pleasure. So it's a great pleasure and honor to introduce Garnet Chan as the new speaker of our colloquium. So Garnet has been around in the tensor network, DMRG, matrix product state community for a long time and really pioneered the use of these tensor networks for use in quantum chemistry. And he has a very distinguished career. He was a professor in Cornell, in Princeton, now in Caltech, and we are really looking forward to what he will tell us today. So please, Garnet, the stage is yours.
All right, thanks, Frank, and well, thanks to two Franks. And you know, it's actually really fun to talk about some of this work, because this is work that is very difficult to talk about in a chemistry context. I never ever talk about, so you know, it's nice to be able to talk about in front of this audience. So the work today that I'm going to describe has been done by, of course, these various people in my group, and these are the current and former group members that contributed. Jen Dong is now a professor in China, but anyway, you'll see these names pop up. Okay, so let me just explain the title of the talk. You know, I've talked about tensor networks beyond models, and so to set the stage, I will just explain what it is that we actually do in my research group. So roughly speaking, our goal is to try and understand ordinary matter, you know, that atoms and molecules and normal materials and so on, at a quantitative level. And as some specific examples of problems that we work on, you know, one of the questions that we try and study is an enzyme problem, namely, you know, how is nitrogen converted into ammonia by a particular enzyme nitrogenase? And there we really want to know the detailed nature of the atomic rearrangement, where the electrons move, and so on and so forth in this catalytic pathway. Another problem that we work on that's more in the more material setting is related to high temperature superconductivity. And there, the aspect of the problem we're focused on is, you know, how is TC related to the atomic structure? You know, do different combinations of the elements yield higher TCs or lower TCs, and can we push it up even further? So it's clear that, you know, the answers to these questions, you know, by the very nature, are things that can't be answered, you know, with simplified models, or at least can't be fully answered by simplified models. So it's not a question of universal physics. It's these are questions where all the details matter. Now, for the purposes of this talk, the specific sort of equations that I'm going to be trying to solve are going to be the equations of the electronic structure, determining the quantum state of the electrons in the above problems. And there, the Hamiltonian that you're interested in is the electronic Hamiltonian. So there are the usual energy contributions, you know, kinetic energy, the nuclei create an external potential, and the electrons interact via a Coulomb interaction. And then there is some additional sort of constant term, the energy that comes from the classical configuration of the nuclei. The scale of this problem, in order to obtain meaningful answers in these example problems, is roughly the following. You know, in this enzyme case, it's reasonable to cut out this kind of a small inner region where all the quantum mechanics is very important. And that can be relatively modest in size, you know, maybe a few dozen to perhaps a few hundred atoms. And then you're treating on the order of hundreds to thousands of electrons. On the right-hand side, the superconductivity is, of course, a bulk phenomenon. And in that case, you need to really treat quite a lot of stuff. At the minimum, you know, hundreds of atoms and certainly thousands of electrons. So there are many techniques that are used in these types of quantitative simulations of the electronic structure. And in my own group, you know, tensor networks is a subgroup, and we use many different tools because different tools are appropriate for different problems. But it's fair to say that, you know, all the different classical methods have a kind of domain where they're good and a domain where they're bad. And if we think about, say, diagrammatic methods, and there's many things that fall into this category, you know, these are perhaps the most widely used methods for very accurate simulations of materials, and they're often very fast, but they tend to break down in some regimes. And so, for example, they're very good close to a classically ordered state, and you know, when you get to a frustrated state, then they either become poor or they don't, or they sometimes fail. Or similarly, if you look at Monte Carlo methods, say a flavor of quantum Monte Carlo, diffusion Monte Carlo, you know, this has no sign problem for bosons. But when you go to fermions, there's a sign problem. And what people then do in practice is you control the sign problem by introducing constraints. that allows you to do the calculation, but it then introduces some bias, which is quite hard to remove in practice. So when trying to think about developing tensor networks for electronic structure, if one tries to understand where it fits into the very large family of different techniques, the interesting thing is that tensor networks, of course, have their natural domain of application, namely they're most suitable for these states without too much entanglement. But it seems, or at least it's postulated, that all ordinary matter or natural matter perhaps lives in this special domain. And so that's the, you of course, all you guys are familiar with this, but this is really what is the, real promise of tensor networks, that they potentially offer a wider domain of application than the other methods. Perhaps they're not always as fast and so on and so forth, but perhaps they're more generally applicable. The flip side to this, though, is that if you actually look at any calculation of electronic structure, in practice, tensor networks are almost not used today, and today's talk is really about trying to change that. There is one exception to the case of when the statement that tensor networks are not used, and that's the case of DMRG, which is, of course, the first tensor network, so to speak. And DMRG is itself an established tool in molecular modeling, in quantum chemistry, and it's part of a family of many tools that people use. Now, I'll just say a few things about DMRG in quantum chemistry, though that's not the main topic today. The way in which it works is really the following. You take your Hamiltonian, which is defined the continuum, and to do a calculation, you have to discretize it. And the way you discretize it is you introduce some three-dimensional functions, we call them orbitals, motivated by physical considerations, and then you convert the Hamiltonian into something parameterized by its matrix elements. And the matrix elements are very complicated because the problem is, three-dimensional problem without much structure, and the orbitals are very complicated, and so you have these lots and lots of these matrix elements. But leaving that aside, these summations here, you can think of as being summations over some kind of lattice sites with a very complicated interaction, and so one can just apply the DMRG, or at least adapt the standard DMRG algorithm to this scenario. And this is something that has been done now for, in fact, 20 years, starting work from Steve and other early people. And it's, in fact, within a limited domain, a very powerful method. It's powerful in the sense that in the context of quantum chemistry, there are certain problems that you can only treat accurately today with DMRG. But on the other hand, there are natural limitations to the scalar problem that you can treat. And this comes partly from the intrinsic entanglement structure of DMRG, which, as you know, is only efficient in one-dimensional settings. So, you're kind of forcing it to do these more complicated geometries. And it also comes from the way in which discretization is done, because you generate these enormous number of matrix elements. And so you're limited in how fine a discretization or how many orbitals you can use. And so roughly speaking, you can do up to, let's say, 100 electrons, perhaps, if, in a very large scale calculation, about 100 orbitals or 200 spin orbitals if you take into account the spin. But nonetheless, it's a useful method and has practitioners and has its own community. And as a simple example of an application, I'll come back to this nitrogenase problem. Now, for one reason or another, nitrogenase has become a popular system to discuss in more recent years in the context of quantum computing. And for example, there's a well-known paper from the Microsoft team where they made a toy model of nitrogenase, and it's toy in the sense that they cut out a very small number of atoms and they used a very limited discretization, very small basis. But on the basis of this, they proposed a resource estimate for doing phase estimation. And based on these things, they argued that, this simulation could well be the killer app for a quantum computer. But in fact, you can take precisely the Hamiltonian, the model that they wrote down, and you can solve it by DMRG. So you can obtain the ground state energy to essentially the same accuracy of the resource estimates with a modest amount of computation time. So that's all to say that this is indeed a powerful technique, but I won't be talking too much more about it because the limitations are also well understood in terms of both the size of the system you can treat and the number of basis functions or the discretization that you can reach. So what I'm primarily going to focus on today is trying to realize what I think is the full potential, the full promise of tensor networks in problems like the electronic structure problem for which what you really need is true three-dimensional tensor network simulations in the continuum, or at least approaching the continuum limit with long-range interactions. Okay, so those are the challenges. And in the last few years, some members of my group have been working on each one of these. Now, I can't say that we solved all the problems, but we have made some progress, and that's what I will tell you about today. All right, so let's first start with long-range interactions. So long-range interactions present some challenges for tensor network algorithms. And, one is simply that many times when you write down an algorithm, it's formulated specifically for short-range Hamiltonians. TBD is of that form. And so you need to either adapt them or choose algorithms which aren't so sort of range specific. And so far, our strategy has just been to just not use the algorithms which are formulated for short-range Hamiltonians and use ones that are a little bit range independent. For example, if you minimize the energy, you can just take the gradient and do gradient optimization. So that's how we handle that. A second issue, which might not seem an issue in the beginning, but is in fact an issue if you think about it, is that if you were to take, say, a pairwise interaction, like the Coulomb interaction, and you evaluate it term by term, then of course, even in the optimal setting, if you truly evaluate every term, the cost of evaluating it is n squared, where n is the number of sites. Now, that doesn't seem that bad as a scaling, but remember that later we want to take the continuum limit as well. So n can be very large. It may be thousands to millions. And so n squared is really much bigger than n. And so in this context, what do we do? Well, we take into account the fact that this long-range interaction is in fact not arbitrary, but it's very smooth. And this offers the potential to encode or compress it using ideas from tensor network operators. And so this second thing, the first one, gradient optimization, I think you guys will know about. So the second thing is what I will continue talking about now. So let's first think about how you can compress operators in 1D, which is very well known. You basically can compress them by writing them as an MPO or fixed bond dimension. And just to say mechanically how it works, imagine you have some interaction, V depends on some distance between 2 points, I and J. You can write down some MPO with some matrices. And the way in which you think about this approximating the interaction is as follows. There's a matrix that's in the MPO between the operators. And when you multiply out this matrix, it's really generating the transfer matrix or generating sort of a correlation function between the 2 points that decays, in this case, decays exponentially. And so the value of the correlation function between the 2 points is what is being used to approximate the interaction potential. Now, as you increase the dimension of M, then it can cover many types, it has many eigenvalues, the transfer operators, so it can cover many types of exponentials. And so you're approximating this arbitrary interaction in that sense by a sum of exponentials or its discrete Laplace transform. And this is, of course, all standard technology in the one-dimensional world. Now, in principle, this can be done in 2 dimensions as well. And so that's where we started out. It basically works like this, right? So you have 2 operators, between 2 sites, and then your PEPO, the generalization of the MPO, has some additional entries in the tensors, which I'm going to call T. And what these additional entries, this tensor T, is doing is it's encoding a correlation function between the points. And so if we compute the correlation function, it's some function of these 2 coordinates, and the PEPO therefore encodes this interaction where the interaction elements are the correlation function times the operators. Roughly speaking, that's how it works. So this can be done, and you can imagine that you can choose your T's in such a way that you get the interaction you want. Now, one common requirement or desire is that you want the interaction to be isotropic. So if I take the Coulomb potential, for example, it just depends on the modulus of the distance, and it's kind of cylindrical, spherically symmetrical around in that sense. A general correlation function on a lattice, of course, is not isotropic at very short range, but it does become isotropic at large separation. So the way in which you handle this is you insert fictitious sites so that when you end up evaluating your correlation function between 2 physical sites, which are these black dots here, all these fictitious sites mean that on the fictitious partition function, these sites look like they're separated by a long distance. And so then the correlation function looks isotropic. So the end result is that, analogous to in 1D, where you're representing your interaction as a sum of correlation functions, in which in 1D you write down very cleanly as exponentials. In 2D, you can write your interaction down as a sum of these more complicated correlation functions, not strictly exponentials, but roughly speaking, the procedure is the same. And in principle, this means that if you have a fixed bond dimension here, that you can evaluate the energy with long-range interactions with a cost that is order V or order N rather than order N squared. And as like a simple demonstration, in the very first paper, we just decided to minimize the energy of the long-range Heisenberg model using both a PEPO representation of this long-range operator, as well as a brute force summation over all the individual terms to get the energy. And you can see that you minimize to the same result. So in practice, you can achieve this representation. Now, in constructing the correlation functions to represent the operator, there's really a lot of choices, of course, because you can put in many different tensors, which generate many different types of correlation functions. In the context of electronic structure, where the desired interaction is 1 over R in 3 dimensions, there are, however, some particularly nice choices. One thing that we showed was that if I take this tensor matrix elements to not be ordinary numbers, but Grassmann numbers, so this partition function is just some quadratic Grassmann partition function, then this type of correlation function you can write down essentially analytically. It's the inverse of some matrix of the quadratic part of the matrix in this Grassmann integral. And therefore, if I take this matrix to be a discrete representation of the Laplacian, then the correlation function it generates is 1 over R. This is all the propagator associated with del squared. And so then this gives you a very compact representation of the 3D Coulomb interaction in terms of these additional Grassmann tensor network. And similar ideas have been used in the quantum computing context, for example. It's like having a gauge boson, except to communicate the interaction. So in any case, whatever the choice of T, as I've said, in principle, this allows you to simulate long-range interactions in a compressed and efficient way. But what we found was that in practice, working with PEPOs is in fact very expensive. But working with PEPOs of any non-trivial bond dimension makes the PEPS calculation very hard. So what I'm going to show you next is actually a much simpler way to do this that is much, much cheaper than using a full PEPO. Okay, so the simpler approach is described in this paper, but it involves representing the Hamiltonian not as a PEPO, but as a sum of what we called in the paper generalized MPOs, but which might be recognized in other contexts as comb tensor operators. So what I mean by this is you write your Hamiltonian, and let's imagine the problem is a 2D lattice. I write it as a sum of terms. And so the first term is just an MPO on the first row, but then you have these combs that extend or eventually across the whole lattice. And I think it's presumably clear to everyone that working with taking the expectation value of combs is actually much, much cheaper than taking a value of PEPO because you don't have so many bonds. And roughly speaking, contracting a comb is the cost of contracting a single MPO using boundary methods. Now, the key thing about these comb tensor operators is they provide a very efficient representation of a certain type of isotropic long-range interaction. In particular, if you imagine a Gaussian isotropic long-range interaction, so this interaction matrix here is just a Gaussian, then a Gaussian has a nice property that it factors into Gaussians on the X and the Y directions. And so what you can set up then is that you can set up your comb so that the columns of the comb are generating a factor that is a Gaussian along the Y-axis, and the rows of the comb are generating a factor that is a Gaussian along the X-axis. And then the combination then of the rows and the columns as you traverse the comb then generates naturally the isotropic e to the minus alpha R squared interaction. And clearly then if I sum over all the combs, I generate all e to the minus alpha pairwise interactions between all the sites. So that's a basic idea. And you know, of course, one doesn't necessarily care about Gaussian isotropic interactions, but you can always expand an arbitrary interaction as a sum of Gaussians. Then each Gaussian then is a sum of combs or sum of gMPOs. Just to show you that this expansion is quite rapidly convergent, I show here just a simple demonstration of a trivial long-range trivial Hamiltonian, but with a long-range 1/Rij Hamiltonian. And here I evaluate the expectation value of this Hamiltonian with different trial states. These are not the ground state. This is a trivial Hamiltonian, has a trivial ground state, but some trial states. And there's some PowerPoint issue with the resolution here, but you see that the error in the energy as a function of the number of Gaussians drops very rapidly. So it drops sort of exponentially. So the Gaussian representation, even for 1/R, is very efficient. Okay, so that's just a toy, and let's now look at perhaps a more realistic application. And so this is where I turn to some cold atom physics. So I said in the abstract that I was going to show applications from cold atom physics. I'm not a cold physicist at all, but it just turns out that there are some simpler models there that kind of naturally fit the first demonstration. So most of the things I'm going to show are from cold atom physics. So we're going to study the problem of the phases of Rydberg atoms in an array. What a Rydberg atom array is, you basically make these neutral atoms and you hold them in a trap and you space them out so they're in an array. And the atoms can be excited by a laser, so they go from the ground state into a Rydberg state, an excited state. And when they're in the excited state, they interact by dipolar, not dipolar interaction, but they interact via 1/R26 interaction. So you could write down the Hamiltonian that describes these Rydberg atom arrays, and it looks a bit like this. Basically, there's a driving term, which is like a chemical potential, which is making more and more excitations. There's the interaction term between the excitations, that is a 1/R6 character. And then there's a non-diagonal term, which is the relaxation from the excited state, the Rydberg state, back to the ground state. So it's an off-diagonal term. So there's been a lot of interest in using these Rydberg arrays for various things, quantum information processing, quantum simulation. But a natural question is, if you just set up these arrays, you know, what is the natural ground state if I tune the different parameters by the laser strength and so on and so forth? So, so in one dimension, this problem has been answered recently by Andreas Leuchli, rather than Leuchli. And so they compute the phase diagram. The details are not so important, but on the x-axis, on the left-hand side, the system becomes more quantum. The right-hand side, the Hamiltonian is more classical. And so on the right-hand side, basically, it's very classic. You just have classical repulsions of the 1/R6 type, and the system just crystallizes. And then depending on the chemical potential, the density, you get different packing fractions of the crystals. On the left-hand side, when you have very strong off-diagonal terms and it disorders, and then there's these gray regions where, interestingly, there's a kind of floating phase where the crystal melts a bit, but it doesn't completely disorder, and you have this gapless phase. Now, 1D is great, but what I'm told, and how I got into this is talking to the experimental colleagues, is that these experimental techniques are now so sophisticated that they're really building 2D arrays, and they're building them with like hundreds of atoms and so on, or 100 atoms. So then the question becomes, what's a 2D phase diagram? And so just earlier this year, people in Misha Lukin and Subir Sajdev's groups decided to compute phase diagram from DMRG. And there they use a standard cylindrical geometry. And they treated the long-range interactions, but they cut them off after a lattice distance of 2. So they do some non-local interactions, but it's strictly cut off. And the phase diagram they see is essentially this is from their paper. Again, sort of left is more quantum, right is more classical. And so one sees a variety of different crystalline states on the right-hand side. And you see these pictures, which are showing things that look like crystals of different packings. But then there are also these plots here where you have these weird blue colors. So yellow and black means there's either an excitation or not, but then these blues here mean that there's kind of a bit of an excitation. And these are described as quantum phases. You know, intriguingly, the atoms don't crystallize, but they sort of delocalize, but they don't completely melt either. Okay, so this is all great, but there are some limitations in this study, both from the size of the cylinder, because it's DMRG, and also the range of the interaction. So this is something that we now thought, okay, let's just do it by PEPS. So we did PEPS calculations now, large squares now, and we put in all the long-range interactions using this comb tensor network operator or gMPO technique. So no truncation. And so then we can ask, what do we see? So this is the original phase diagram, and indeed at the bottom of the phase diagram, we see these crystalline states, right? So this is a checkerboard geometry, and this is a star geometry. But when we move higher up in the phase diagram, we see actually very big differences. So all these ordered phases actually now disappear; they become disordered. And the reason is, you could say, well, why is this happening? Well, if we turn the really long-range part of the interaction off, so we truncate it the same way as in the DMRG paper, you recover the same phase diagram as in the DMRG paper. But when you turn the long-range interactions off, they disappear. And so what's happening is that there's actually, when you go higher up, there are more and more types of classical crystal packings, and they all get really close in energy. So the very small long-range terms melt the crystal already. That's essentially what happens. Then if I move to the right of the phase diagram, so to parameter ranges that are off the original range, you discover new types of crystals. And then you can also discover new types of quantum phases as well. So we call this a quantum pill phase. So, yes.
Question, their truncation of the longer range part of the interaction, was that done in a clever way? It wasn't just a cutoff, or?
It was just a cutoff.
So then you have a sharp edge, which could give all sorts of artifacts.
That's also true, yeah. So I don't know why, but that's just what they did. We actually went back and did DMRG with all the interactions because, I mean, why not, right? And there's no reason not to do that. And then the results, PEPS and DMRG results are very consistent. But for some reason, I think they just assumed that the interaction is very small because it dies like 1 over r to 6, which is true. It is very small, these terms, but the competing.
I mean, if you think about entanglement caused by a long range thing, if it's too smooth, it can't do anything. But if there's any sort of sharp cutoff, it can try to cause entanglement at that distance.
Yeah, right. Like I think, as you pointed out, I think in other contexts that if it's long range but very smooth in some sense because it's not changing very much, then the long range tail is like just a chemical potential shift, right? We haven't analyzed the results of the truncated interaction through that lens, but I mean, yes, there's certainly a difference.
Actually, I have one follow-up question. So when you were doing DMRG with the full long-range interactions, how did those calculations compare to the PEPS calculation in terms of the accuracy and?
Yeah, so you see, as it turns out, this problem is not that interesting in tensor network language because you see the phases are very classical. With PEPS, you can completely converge to, I think, 4 decimal places with a bond dimension of 4. Now, DMRG, you need larger bond dimension because of the cylinder, but you don't need very large bond dimensions on, say, an 8 by 15 cylinder to converge. I don't remember the precise number, but it's definitely not pushing the limit of modern DMRG technology.
Okay.
But also a big difference could be that in DMRG you actually take periodic boundary conditions, and in PEPS you probably take open boundary conditions, no?
Yeah, so that's correct. So a difference with their original paper, they use periodic boundary conditions are really unnatural for a trap because the trap is a finite trap. But when we did DMRG, we also compared to using open boundary conditions. So I don't show any of that data there, but we can sort of consistent. There is an important question: are the boundary conditions causing the difference, or is it the long-range interactions? And what we have seen in the DMRG simulations where we've done the same open boundary conditions is that it's a long-range interaction that is making the bigger difference. But you're definitely right that there are lots of boundary effects as well. You can see that the excitations like to gather at the boundaries. So this is important. So, for the actual physical experiment, the relevant thing is to have boundaries. That's because you make a trap. But yeah, the question of really what's the bulk phase when it goes to infinity is also, of course, important. So so, this is just a demonstration that for us, the technology is working, but, it also happens to show that an example where long-range interactions do modify the phase diagram, and they introduce, in fact, new phases. Yeah, okay. So, so that's what I'm going to say about long-range interactions. I mean, that's where we are, so we have technology that we can apply. This is the first application, but it's not the most interesting one, and we will come to more interesting problems in the future. And now let me talk about the continuum limit. Okay, so the continuum is, I think we all recognize, really a limit of something. And, concretely, you see this limit as follows, right? So let's imagine you have hopping on a lattice and you have some discretization epsilon. And you can imagine making epsilon smaller. So if you start with a lattice Hamiltonian like this, describing hopping, nearest neighbor hopping, you make epsilon smaller, and then eventually you can identify this as a discrete version of the Laplacian, and there's some volume element with an epsilon, so you can define your new creation operators to take into account this volume element, and that's the continuum Hamiltonian. Now, that's the sort of continuum limit of the Hamiltonian, but in terms of the continuum limit of the state, in which case there's an MPS, say, this is a 1D problem, there's sort of two ways in which one can take the continuum. One is to do a numerical limit, right? So a numerical continuum limit. And in essence, what you're doing there is you're doing calculations, each of which is at a fixed discretization, and then you take your quantities and you extrapolate them to the continuum limit. Okay, so you start with this Hamiltonian and you just do it for many different epsilons, and then you extrapolate your results. So, so that's been done for quite some time now. Early papers from one of the early papers is this paper here with Steve, and the technology has now become, I would say, quite mature. So if one was to ask what's the state of the art, an example of the state of the art are these slice spaces calculations, where the continuum limit is taken in one dimension, and there's a basis representation, a continuous function representation, x and y. And so in this way, you can sort of efficiently represent cylindrical three-dimensional problems. And taking the continuum limit in this case allows you to obtain really accurate or nearly exact solutions of a real electronic structure problem, one involving, I mean, it's an artificial problem, but still it's really the real atoms, hydrogen atoms, and obtain a near exact solution in the continuum limit. Now, the other approach is to take the limit analytically, where you sort of write down the mathematical form that one should have. And many of you are familiar with this. And the reason is a little bit like this, right? So you take, say, if you have two particles, you want to write down the MPS that gives you the amplitude for two particles to be at 2 points. And this is just some finite number in the continuum limit. And one can imagine the process like this, where you're creating a particle at 2 points, and then your MPS has all these matrices in between, which are generating the amplitude. But because you're going to be multiplying a lot of matrices together, and they have to multiply to a finite result, then those matrices have to have a special structure. They all have to be almost the identity. Otherwise, they don't multiply out to a finite number. And similarly, one can associate some amplitudes with the creation events themselves. And taking the continuum limit of the product of 1 plus epsilon q, gives you an exponential of q to the x. And so in this way, one can write down a very nice analytical looking thing in terms of path integral involving the exponential of q and r. And this is the continuous matrix product state that Frank wrote down, and Frank Ignacio wrote down, I guess, 10 years ago now. So it's really very nice, and as a formalism, in terms of the numerics, I'm not an expert. We have not done these numerics myself, but my impression is that the numerics are less well developed. And the state of the art, as far as I see, is these papers, for example, by Giffrey's group, where in this case they did the calculation of interacting bosons of the delta function in a periodic potential. Those of you familiar with the Lieb-Liniger model, the primary difference is that there's this periodic potential, so you don't have just one tensor. The tensor really has a coordinate dependence now. But this is kind of clearly, less advanced than the numerical limit calculations. And as they stated in their work, this is partly because working with continuum MPS numerically is a much more delicate problem prospect than working on the lattice. Okay, but in any case, we're not trying to do MPS what we want to do is more general tensor networks. And so let me now talk about Continuum PEPS. So there's been quite a lot of papers on Continuum PEPS that I've seen. And the basic idea of the analytical continuum limit, which is what most papers have been talking about, is sort of the same as for the Continuum MPS. You want to write down these matrices that generate essentially the wave function associated with the creation events. And all these, but these are now tensors, and all these tensors must somehow be close to 1. But what is 1 as a tensor, right? It's a little bit ambiguous. And I think some progress along this direction, it seems nice to my eyes, is from this recent paper by Antoine Tilloy and Chirac, which proposes, at least some plausible versions of what this identity tensor could look like. But speaking from a numericist perspective, given that continuous MPS are quite hard to work with, and these continuous PEPs are even more complicated, it's I think an open question whether numerics are very practical here. So what we've done to study problems in the continuum is just to take the numerical continuum limit. And this is essentially what I'm going to talk about next, and is what is described in this paper here. Okay, so conceptually, the numerical continuum limit is very straightforward, right? You just write down PEPs on a very fine grid and make the grid as fine as possible and extrapolate. And because in a fine grid, we call it PEPS-fine, just to remind the people that's in a fine grid. And so that's the PEPS. It's got lots and lots of tensors, and we want to make epsilon small. So it conceptually is very simple. But practically speaking, it's not that simple. And that's because the optimization problem becomes quite difficult. Typically, you just get stuck when you have a lot of tensors. This is an example of an optimization trace where you use standard methodology, simple update and full update. And full update's usually really quite good. But just for this problem of free fermions confined in the box, simple update starts about here, and then you do full update, with a larger time step, and do full update with, quite small time step, and then you're just stuck very, very far from the exact result. Now, this behavior has been seen in the Continuum MPS, and both in the numerical limit and analytical limit. So it's really expected behavior. And there, what you do is to avoid getting stuck, you use the fact that you can do that most of the basic physics is actually already established on a coarser scale. And so you could do calculations on coarser lattices and then use them to make guesses or extrapolate to finer lattices. And so that's essentially what our strategy is for the PEPs as well. So this leads to a type of multi-grid framework where you do calculations on different scales of lattices and you interpolate results down. And this work is inspired by multi-grid and MPS, although the ingredients in PEPs are obviously more complicated. So it basically works a bit like this. So you do a calculation on the coarse lattice, and then you interpolate by expanding with isometries. And this, of course, doubles the lattice size. And you can variously optimize to make these isometries, isometries good ones. But this is not a PEPS. So you somehow have to convert this into a PEPS in the finer lattice. And for that, you need to split things. And so you have to, for example, double the number of bonds. So you insert some isometries along the bonds. And then you have to generate, four times as many tensors. So you do a series of SVDs to split them into 4 tensors. So in this way, you can project or interpolate from the coarse lattice to the finer lattice, and then you re-optimize your tensors, and then you do it again. In this way, you can sort of get to exponentially fine scales.
Wait, Garnet,
yeah.
the splitting part of that,
yes,
is that as simple as it sounded like when you just described it? I mean,
yeah, you can. It is more or less. You basically. You group these things. So first you have to split them into so you first split them left and right, and then you take the left and right piece and then split them up and down. Okay, and so and to split them left and right, you have to just group these indices and split them left and right. And then to split them up and down, you have to insert 2 isometries and then SVD those up and down. And they give like 4 tensors, with some significant error in the splitting map. And that you can then, in principle, optimize relative to this original tensor to further improve them. In practice, we actually don't usually do the optimization, but you'll see the value of that error in a little bit.
Yeah, sorry, I also have a question. So why do you use isometries? Because in principle, these could be arbitrary tensors, no? There's no...
They could be arbitrary tensors, yeah. So there's no real reason. Isometries are quite numerically well behaved, you know, but otherwise they don't have any strong reason. So this way, you know, it becomes practical optimized law of tensors. And so you can definitely do calculations with more than 1,000 tensors, and I'll show those calculations later. So just as a simple benchmark, we can do 3 fermions in a finite box. This is kind of just showing all the different components of multigrid. So this is a calculation of the coarse grid where we optimize the isometry to project onto the grid below. Then we do the split. And this split, if we do 4 SVDs, it's approximate, so the energy goes up. You know, it's not a perfect split. And then we optimize on the finer grid, and the energy goes down, and we can basically get, rather than being stuck, we can get to the correct result. Now, you know, how well can you do for 3 fermions in a finite box in the continuum limit? Now, 3 fermions is of course very hard. Even in a finite box, if we take a box that's 6 by 6, the gap is on the order of 1/6. So it's not a very large gap. It's not very easy for PEPS, but you can do okay. So here we do calculations up to bond dimension 12 fermions using U1 symmetry, and with extrapolations with bond dimension and so on and so forth. You know, these are the obviously analytical continuum results, and you can get to a few tenths of a % inaccuracy for this otherwise rather trivial problem. All right, so let's now look at a more realistic application, and then this is again going to be taken from cold atom problems, and it's the problem of the unitary Fermi gas or Fermi gas in 2 dimensions. So this is a gas with just 2 fermions, like spin up and spin down, and the Fermi gas is one which you can realize in the BEC condensates. You basically apply a laser, induce a Feshbach resonance with very short range interaction, and make the gas very dilute. And so on that scale, it looks like a delta function interaction. And you know, the interaction there, the Hamiltonian then basically looks like this. The interaction between the atoms is attractive. So if you take 2 of these fermions, just 2 of them, they will bind. And that's a characteristic binding energy, epsilon B. And so generally, most of the time when people discuss the unitary gas, they discuss everything in terms of a dimensionless parameter, which is the ratio of the binding energy essentially to the kinetic energy. So epsilon B to the Fermi energy, and it's this parameter eta. Okay, now the unitary limit or the unitary parameter range is when the number of spin up and spin down fermions is the same. And this presents a number of analytical and numerical simplifications. Analytically, in this limit, if you take the energy per particle in the thermodynamic limit, it becomes proportional becomes proportional to the density of the system. So that means the energy per particle divided by the density, which is the left-hand side, is just some number which depends on this dimensionless interaction string. Right? So it becomes easy to talk about if you take this continuum and thermodynamic limit. In the numerical side, it's also considered to be, there's also a simplification because determinant Monte Carlo methods like AFQMC don't have a sign problem because of the sign of the interaction and this equal balance. And so in principle, one can generate exact results. Otherwise, the unitary limit is not actually that interesting. But what one, I think, cares about in more modern times is what happens away from unitarity. But for benchmarking exercise, it's very good because there's just a lot of data on it. And so this is what we're going to use for benchmarking. Okay, so I'm going to compare the PEPS, multigrid PEPS or PEPS-fine with some high quality AFQMC data. There is some even higher quality AFQMC data that's a bit more recent than the stuff I'm showing here, but this data is up there in quality. We use it because they computed a quantity that's a little bit easier for us to compare against. Here are some results for that function of eta, which is the energy divided by the number of electrons divided by the density in the thermodynamic and continuum limits. And I won't go into the details of all these plots, but the take-home message is, although QMC is exact, because you have to take the continuum and the thermodynamic limit, it's not actually very easy to get this number f of eta. because you have to take lots and lots of sites in the continuum and you treat lots and lots of particles. And so here are calculations which have been extrapolated to the continuum limit using grids up to 40 by 40, where you also try and extrapolate the number of electrons as well. And you can see there's still quite a lot of uncertainty due to the range of electrons that have been due to this thermodynamic extrapolation. And the tensor network calculations were done on grids ranging from 4 by 4 down to 32 by 32, which is over 1,000 sites. And one can extrapolate to a similar number. And both there's uncertainty in both results, but the uncertainty is comparable. And what is really interesting is this is like the best case for QMC. So I think this is quite promising because even in this like optimal case for QMC, these continuum tensor network calculations are actually quite competitive. But what we can now do and what we're currently running calculations on are the systems that are not at the unitary limit where you have the sign problem in QMC. Okay, so that's what I want to say about the continuum limit. And I have no idea what time it is, but I have about 5 more minutes of stuff to talk about general 3D tensor network contractions. And this work is very, very preliminary, but I can give you the spirit of what's going on. Okay, so we think that the way to think about generating 3D tensor network contractions is really in the context of understanding how to contract general tensor network graphs. And the reason is the following, which is, in 2D, there's already many different contraction techniques, and 3D offers potentially even more choices. And in 2D, we don't often ask so much which is the best one, but in 3D, thinking about which is the optimal way is, I think, an important question. But one problem is that it's not actually very easy to comprehensively test all these choices because when you implement these algorithms, they implement in very specific ways. And there isn't like just some simple parameter that you change in your implementation that converts boundary to TRG. They're just two different programs. But one motivation for why we should really optimize heuristically over many different contraction and approximation strategies is offered by the limiting case of exact contraction. So in the exact contraction, where you don't have any compression, we know that optimizing the structure of the contraction yields enormous improvements. And there are very kind of clear examples of this in circuit contraction. So for example, in the Google Sycamore supremacy experiments, they created circuits which they argued would take 10,000 years to contract using the largest supercomputer in the world. But if you simply optimize the structure of the tensor network contraction, this time can reduce to a matter of a couple of weeks, as has been demonstrated by Johnny and also more recently by the Alibaba group extending these original ideas. And so what we're trying to do first is to just create a kind of framework in which one can think about considering a very wide variety of different tensor network contractions. And then on top of that, one can build heuristics to optimize not the exact contraction, but the approximate tensor network contraction, really for arbitrary graphs. But hopefully in this way, we can also discover the right way to do structured 3-dimensional grids. And this is a popular topic, so there are other people working on these things today. Okay, so generally the structure of approximate contractions is the following. I mean, you choose some way in which you're going to contract things together, and you have to insert some compressions. And both the order of contraction is very important, and the order of compression is very important. So roughly speaking, one starts with some graph, and from here you connect up the tensors to generate some expression tree of contraction. So that's the contraction tree. And then one has to decide how to insert compressions in between the branches of the tree. So there's many ways to generate contraction trees, but the simplest way is to just use a spanning tree of the original graph. And in that case, all the intermediate tensors in some sense can be associated with nodes of the original graph. And then you can write graph algorithms which generate many different spanning trees, which then correspond to different types of tensor network contraction strategies. And the order of contraction can also be defined quite simply algorithmically by using a graph distance on this tree. So just concretely, I can say, let's generate a spanning tree starting from a central site and just build it outwards. So you generate, these colors illustrate the tree growing outwards, and then you contract using the distance metric from the furthest point back inwards. And so this generates a type of boundary contraction style, which is like a sphere, coming into a point, right? Or you could say, let's generate the spanning tree starting from a corner and use a slightly different notion of distance. And then that reproduces the MPS boundary contraction, where you contract columns along into the point. So this gives us just an easy way to tweak between different scenarios. And one can also adapt these by considering more general trees, more general contraction trees to also cover TRG and other things like that. Then one inserts compressions once you've decided the sequence of orders, and I think everyone understands you can compress using more or less information from the environment. So you can use the local environment, or you can use the full environment, and one can code this in. So we're at the stage where we've basically implemented all these things and we're ready to try them out. And on top of that, develop some heuristic optimization of the contraction strategy. But just as a very simple demonstration, this is a contraction of 3D Ising partition function. The lattice size here is chosen here because to generate exact data is actually quite expensive for finite lattice. So this was the smallest, this was just something we could generate exact data on relatively easily. And the important point is I'm going to show a contraction where we don't really say anything about the cubic structure of lattice at all. We just generate a spanning tree using some metrics so that it looks a bit like a boundary contraction and do automatic compression. And so this is just the error in the partition function. So the Ising model is a function of temperature, critical temperature is near 0.2, and as a function of chi, you can obviously converge a partition function very accurately. And this is using the full environment for small chi, and indeed the results improve as you expect when you put in more boundary information. So it's no new physics or no new results in this sense, but this is just to show that the code is ready so that we can start thinking about how to build heuristic graph optimization strategies on top. So that's pretty much all I wanted to say. So let me just conclude. So, main message that I want to convey and what we're really thinking about as an overall theme is that realizing, I think, what is this immense promise of tensor networks in principle, right? But in practice for quantitative materials and molecular science requires us to tackle a few things. And we're working on them. And that's really the story of today. A brief shout out to this fabulous library that was developed by Johnny. It's a library for both tensor networks and circuit simulations, and you can do the Sycamore circuit hypercontraction paths using this library and associated libraries. So it's really quite fun to use. And this work's been funded by various agencies, the Science Foundation and Amazon. So, and with that, thanks.
Thanks a lot, Garnet, for this great talk. I'm sure there are some questions. So let me maybe start with the question. So, so in the beginning of your talk, you were interested, or you were showing us how to get long-range interactions, and especially Coulomb interactions and all this. So, but physically, you would expect that this power law interactions are not really happening in a real material. No, you would expect that they're always screened.
Yes, yes.
So
they are.
So,
but how do you calculate the screening, right? So the real question is.
That's the question I wanted to ask you.
Yeah. So I mean, so you can start from a model of the screening or something like that. But if one's really going like full ab initio first principles, the screening has to emerge from the calculation itself. And at the level of doing the normal practice in ab initio molecular material science is that you have to calculate the screening as part of the calculation itself, right? You cannot just get it from somewhere. But so yeah, so I think that's why we're not putting in screen interactions and stuff. Of course, in an insulator, it's not screened to be particularly slow. It's just screened with a dielectric constant, roughly speaking. So you still have a long range tail.
So any other questions?
Maybe just before tackling the big open question in quantum chemistry, what do you think are the main bottlenecks right now? Like, is it the representation of the ground state, or like the methods for contracting it? I mean, where do you see the main
Yeah, well, I think, we define this as 3 steps, right? Long-range interactions, continuum. I mean, long-range interactions is the thing we've been working on longest. I mean, I think that's pretty much there in terms of representations. I think the biggest challenge in long-range interactions is when you're doing gradient optimization, really what's the best way to do gradient optimization with tensor networks? So what we find happens more with long-range interactions, this representation is, let's say you just follow the gradient. You can often optimize yourself off a cliff because the gradient optimization is somehow not as stable. You need very large chi, and so that's some technical issue, but we see it actually happen much more with this long range representation than if you're doing the Heisenberg model. In the context of continuum, well, I mean, we just did this first model, like the Fermi gas. So I mean, what we're aiming to do is the next real calculation is the electron gas. So that means like a 2D continuum model, but not with the delta function, but the Coulomb interaction. We'll just see how it works, right? I mean, there may be unexpected problems. And then in 3D, I think it's a big question, right? What's the best way to do approximate tensor contraction? I mean, it applies to approximate circuit simulation and all this kind of stuff. So, I don't have any, it's too early on. I don't have any magic feeling for what, I think there's problems to solve, basically. And I don't know what the answers are, but we're just getting started.
Well, the higher the dimension, I would think that the more it makes sense to actually make use of translation invariance, because the higher the dimension, the larger the boundary becomes of your system. No? So that's basically the main reason I think that most people, when they do PEPS, they actually do infinite PEPS, because the boundaries are much smaller. The boundaries is really a problem, and then certainly if you go to 3D, the boundary is so much larger than the bulk. If you have small systems, that this is a huge bottleneck.
But we don't have we don't always have the option of choosing translational invariance. So, but I mean, of course, if it's there, that's a good thing to use. But generally, we don't have that in the problems that we care about due to the external potential, which breaks the translation.
Yeah.
Yeah, Garnet, I have a question.
Sure.
So in the end, you talk about approximations and tensor network contractions.
Yes.
So these, I feel like these types of things can work very well if you just want to evaluate a network once. But if you have this as part of an optimization algorithm, then you can have like instabilities that feed back on themselves. So even small errors can run away and things like that. Do you have any comment?
No, I mean, I agree. When I was saying that you can optimize yourself off a cliff, this is exactly what I'm referring to, right? Somehow the optimizer discovers that chi is insufficient along some direction of optimization, you fall off.
And exploits it.
And exploits it. That I think is a big problem. When we're doing these Rydberg atom simulations, there is, Matt, who worked very hard on it, had to do quite a lot of hand-holding of the optimizer to make sure that, it doesn't fall off. And I think that's a really big problem. I don't really have a good answer. Right now, we just rely on making chi big, right?
I'm actually glad to hear that, because that's my own experience as well. I'm glad I'm not the only one who.
Well, I'm glad to hear that you have this experience, because it's not a widely reported experience. Yeah, it's not a widely reported experience. So first we're like,
you don't write a paper saying how you failed to introduce valid approximations.
Yeah,
maybe.
But well, it's good to hear that we all share the same.
Thanks, Garnet.
Yeah. If I may continue in this, when you're talking about chi in this context of gradient optimization, with this you mean the chi that you need for the environment which you use to compute the gradient. Is that correct?
Yeah, that's right. Yeah.
Okay.
Yeah, all the intermediate compressions, right?
Because if I understand correctly, the whole formalism of automatic differentiation tells you that you should be able to compute the gradient of well, you already make approximations with higher dimensional tensor networks in computing the energy.
Yeah, so automatic differentiation is, which is what we use, is differentiating the approximation, right?
Yes.
But it's not stable in the sense that the energy is not bounded, you know, in many cases.
Okay.
So, you know, if we do all these very simple models like Heisenberg and so on, we don't see any problems, right? But when we start going to these more complicated things, you just, as I say, unless you make chi really large, you just get minus, you know, not infinity, but you get minus very large numbers. It's very, very frustrating. Another big question, I suppose, is if you rely on gradient optimization, maybe you guys have some, you know, how do you initialize your tensors? So when you do, you know, simple update or something like that, there's just a natural way that the bond dimension is growing. But just directly gradient optimization, right? You have to start from, fill up your tensors from something in the beginning. And when you have a lot of them, it's very hard to do this well. You multiply out, you know, 1,000 tensors. So that's another practical problem we've had. And there are various practical things. You might do simple update with a shorter range potential, and so, you know, there are many things you can imagine, but we haven't found a really good answer to that problem.
Garnet, back to the question of the, you know, this behavior of the long-range interactions.
Yeah.
I wonder how much universality there is in terms of sort of, you know, so you work really hard to get a 1/r fall off.
Yeah.
Okay, but suppose you take the same realistic system, you change the 1/r to fall off with some sort of screening, and you do everything the same sort of effect on the nuclear interaction, so that everything is sort of changed at long distance. And then the question is, how much does the system notice? And we have some recent calculations in the hydrogen chain, where my student Randy is working with, you know, you sort of go through this intermediate stage where you have a long range Hubbard model, and then you optimize to try to get an interaction that falls off very quickly, like 3 or 4 sites.
Yeah.
But the ground state that you get with that interaction is the same as the ground state with the long range interaction. And so there has to be an optimization of the Hamiltonian to get the same ground state. But then you find that you can get the same ground state, you know, with a fidelity that's above 99%, you know, very accurate. And so I'm just sort of wondering how much being faithful to the correct 1/r fall off matters in practice, and also whether you could put in the correct fall off just at the end after you've optimized everything.
Yeah, I mean, that's like a kind of fundamental question. The one thing I would point out is there is a difference between the way in which the external potential is 1/r and the Coulomb interaction is 1/r, because one is a 1 particle potential, and the long-range Coulomb interaction is still a 1/r12 interaction. It generates fluctuations that are not of the same kind as from the external, just the 1/r tail of the external potential. But at the level of mean field, right, where the way in which the long-range Coulomb interaction just is like some classical electrostatic energy, you know, then the two do compensate each other. So the difference is that there are phenomena associated with these long-range 1/r, like these plasmon oscillations and so on, that I think will be missed in some, you know, in some approaches. But
right. There may be, you know, there are certain phenomena that you would certainly need it, and others that
where you probably
may be frozen out.
Yeah, that's right. Yeah, so I think in many other cases, just you know, at the level of mean field electrostatics, yeah, they cancel basically. Or there's definitely a lot of you know, optimization tweaks one can do, right? I mean, you just do part of the interaction by PEPS and just add on the static mean field for the long range contribution. These kinds of things can all be done in the future, I think.
Okay, so are there
hello, I might have a question.
Yes, please.
If there's time. So I'm a bit curious about. So when you are optimizing the finite networks, right? Because essentially in all the cases, these are finite networks which you optimize by gradients, right?
Yes.
And so my question would be the following, that, well, you contract your network producing the expectation value of the energy, and then you might run your auto differentiation on top of it to get the gradient. And I would be curious whether you are trying to change the contraction order, or the actual details of the contraction order in computation of the energy, or you always contract in the same way the network in the subsequent iterations when you optimize with the gradient. You see my question?
Yeah, I mean, so right now we just have a fixed contraction pattern for the energy and the gradient, and it's just fixed. Mm-hmm. I think there are sort of things that you can do where you could assemble the energy. Actually, typically when you compute the energy in a finite system, you compute it as a set of local expectation values, and each of those local expectation values is sort of contracting to a point, and so you're actually computing the total energy, the sum of many different contraction patterns. That's all very natural, but when we take the gradient, we take the gradient of that sum of different contraction patterns. Does that make sense to you?
Yeah, sure. I'm asking for the following reason, that, as you say, you are experiencing this thing, the difficulty in, let's say, if you wish, the gradient optimization seems to be quite difficult to get the handle of, and
it's a bit unstable. Yeah.
For the following reason, that, let's say you optimize the network, you get some expectation values, and then if you switch or change the details of the way in which you actually contract the network, if the expectation values would change significantly or not, or in a sense, if the AD or the gradient optimization didn't lead you to a point which is kind of fragile because it's exploiting the truncation of the particular way you contract the network.
Yeah, so these types of things are, I think, done in like machine learning type ways of things, right? You try to trick your optimizer so it can't like exploit some structure, and you can maybe randomize some things, and it might it might be a way to avoid some of these problems, right? So your network doesn't over optimize to specific, like overfit in some ways, right? I know that some people in my group have thought about some things. I think Johnny in particular has thought about these things, but in the results that we haven't done anything very systematically. I have a sort of slightly older school bias where I'm trying to think, well, let's not do it that way, but maybe that's the way to do it. I mean, yeah, you have to sort of trick your gradient optimizer.
Thank you. Let's say my experience, at least in running the gradient optimization for the infinite two-dimensional PEPS, is that even with the frustration, like in the frustrated magnetic models, I was not experiencing so much troubles with this part of the story, like getting a very, very unstable optimization. But then again, if you exploit the translational invariance, there is very few tensors you have to.
Yeah, they're very.
That
right.
could really ease up the things.
Our experience has been when we read things in the literature that, do the transverse field Ising model or something like that, we hold our breath for a very long time before we believe that it will work for the more complex cases. So we have definitely seen in practice a big difference between simpler models and with short range interaction in particular and more complex things. There do seem to be new numerical pitfalls when you go to more complex problems.
Okay, so maybe this is a good time to wrap up the